Hello! In this video we're going to look at polynomial functions, and in a series of videos we're actually going to look at all the different features and behaviors within our polynomial functions and how those features will allow us to graph our polynomial functions. This first video is to look at identifying our polynomial functions and identifying some key aspects of the equation, such as the degree, the leading term, and the leading coefficient, which we'll see later on are actually pretty important in terms of determining the behavior occurring in our polynomial functions. So the definition of a polynomial function is this equation that we see on the screen, that a sub n x to the nth power plus a to the n minus 1 with x to the n minus 1 and so on, going all the way down to a1 and a0. Essentially what this is showing is that a polynomial function is the addition of many terms of x's raised to various powers. And the key feature and what we're going to be identifying polynomial functions by is that the power that's occurring on my x has to be a non-negative integer. So that means I have a strictly positive whole number powers occurring on my x. And one thing we'll see later on too is that we may have a polynomial function that doesn't quite look, at first glance like it fits this format, that it may just be hiding inside of some operations that would reduce down and create this polynomial function. All of our little a's are there to represent the coefficient of each term. So we usually think of the highest power term as the nth term in our polynomial, and so the coefficient of that is a to the n. And so that n is just really a counter and keeping track of what our power is and our position is in terms of the term in our polynomial. The domain of all of our polynomial functions is all real numbers, so we don't have to worry about any domain restrictions, which is nice. And one key feature we're going to be really focusing on is the degree. That is that n. It's the highest power of x that appears in our whole polynomial. And that's going to be crucial because that's going to help us decide the type of polynomial that we have when it's given to us. So that leading term, the highest powered term for the x, that's going to be really, really crucial for us too. So we call that the leading term because when we write it in this standard kind of written form of a polynomial, we usually like to write the highest degree power of x and then write it in decreasing powers of x. So in that sense, it should be, if we write it in that manner, it should be the very first thing that we write since it's the highest power of x. So we call it the leading term. And the coefficient there, we call the leading coefficient. And that's going to be whatever the constant term is that's multiplying by your x that has that highest power. Oops, too far. All right, so here we have a bunch of equations and we want to figure out if, in fact, they are polynomial functions. If we can identify them as polynomial functions, then we'll go ahead and state the key features, which are our degree, and in a sense, we'll also know our leading coefficient as well. So this example A, it definitely sort of looks like our polynomial function. It's perhaps not written in the format that we're used to, what we call kind of that standard form. So I could very easily rewrite this so it fits that format by rearranging my terms, by allowing the highest power of x, which is x to the fourth, to be leading. And then, I don't have any like x cubed or x squared and x terms that we see. And in truth, they actually are there. We like to kind of think of them as having a coefficient of 0, and that's why we don't see them. So if it's helpful, if we do need to, in fact, write out those terms, you could by including coefficients of 0. Usually we don't, though, because that makes our polynomial very long, and we don't really have those terms there anyway. So we usually don't write them, right? We just write the terms that actually do have non-zero coefficients. So now that it's written in my standard form, we can definitely see it fits the format of a polynomial. So this one is a polynomial. Its degree is the highest power that x is taking on. So here we actually only have one power of x, and its highest power is 4. So we would say this is a 4th degree polynomial. Our leading term would be that negative 3x to the fourth. Our leading coefficient would be negative 3. For b, we look at it and it definitely doesn't quite fit what we expect our polynomial function to look like because of the square root. And so that's a huge tip-off that this doesn't fit as a polynomial. And if we were wanting to really compare it kind of on an even playing field, because we're used to having x being raised to a power, the square root actually is equivalent to a power of 1/2. So I could have also thought of this as x to the 1/2. And there, when we write it that way, we can see it definitely doesn't fit the definition that the power has to be a positive whole number. 1/2 doesn't fit that. So this is not a polynomial function. So I wouldn't go about finding the degree or any other features. One thing to think about too, if you do have operations occurring within your function and they don't kind of fit the typical operations that we see in a polynomial, such as multiplying by a coefficient or your x being raised to a power, that's one way of being kind of clued in that this isn't a polynomial. There is a possibility though that whatever operations are occurring could reduce down or simplify down to a polynomial. So we do want to be careful and kind of jumping the gun, and if you see something that doesn't look quite like a polynomial, assuming that it's not. So for instance, for c, I would probably want to say, no, it's not a polynomial because I see division happening. But division could potentially simplify down to a polynomial. That is possible. And so we may want to explore that before we say no, that it is not. So how I would simplify this, this is actually a rational function here, is I'd have to factor it. And it actually is factorable. These are maybe challenging factorizations for us. I have a difference of cubes on the bottom, which could go ahead and factor. So this would be positive 1x and plus 1. And then the top is kind of like a difference of squareds. 2 is not maybe a square that we think of right away, but I could think of it as the square root of 2 being squared. If we really wanted to factor this, that's kind of a trick that we could pull to get it to factor. The obvious thing, hopefully, that we can notice is that there is no common factor on the top or the bottom that would allow this to cancel out and reduce down to a polynomial. So although we gave it our college try, this one is still not a polynomial. Now D, again, we may be tempted to say it's not a polynomial because I don't see any x's. However, this is actually what we call a constant function, right? G of x is just the function notation to represent y, right? So this is a horizontal line going through the y value of 8, and he actually is considered a polynomial. And how we can kind of introduce that x in there so that we can see it is we can think of this having an x term with a power of 0. Because anything, even x, if you raise it to the 0 power, is by definition a 1. So I'm kind of really just saying 8 times 1, which is 8 again here. But this does count as a polynomial, believe it or not, of 0 degree. So constant functions, those horizontal lines, also count kind of by default as polynomial functions. And our last example, again, I might be tempted to say it's not a polynomial function. It doesn't look like our traditional polynomial in the format. However, again, I may have a polynomial hiding in there. I just need to simplify my answer to find it. So what I'm going to go ahead and do is actually perform this multiplication and see what comes out of that. So I have a binomial being squared, so I need to multiply it by itself, which is actually a foiling process. So when I FOIL out x minus 1 times itself, I'm going to get x squared minus 2x plus 1. And then I need to distribute my negative 2x cubed. So that is negative 2x to the 5th plus 4x to the 4th minus 2x cubed. And probably right about here we can recognize that definitely looks like a polynomial. It has that even the standard writing format that we're used to. So I'm starting with the highest power of x, which is the fifth. Then the next highest power is the fourth, and then x to the third. We can see all the powers of x are positive whole numbers, and so it definitely fits what we would expect to see a polynomial function to look like. So this one is a polynomial function. And the degree, the highest power of x, is 5, so that we say this is a fifth degree polynomial. The leading term is this -2 times x to the fifth. Our leading coefficient would be -2.